Building a distributed system means building for continuous motion. Application requirements are in constant flux, demanding that developers deploy new code daily, if not hourly. To execute these updates without bringing the entire system down, engineering teams rely on rolling upgrades. Instead of turning off the old version and turning on the new one, traffic is gradually shifted from the older instances to the newer ones. This diagram illustrates the mechanical constraint that a rolling upgrade creates. During the deployment window, old application code, version 1, and new application code, version 2, must operate side by side in the exact same environment. This introduces the first requirement for survival: backward compatibility. The new version 2 code receives a packet written by the older version 1 code, and it must be able to read and process that data without errors. The system also requires forward compatibility. The old version 1 code is still running, and when it receives a larger payload with new fields from a version 2 node, it must extract the core data it understands and safely ignore the additions without crashing. These simultaneous constraints make evolvability a strict mechanical necessity. A system stays online only if its data structures change without breaking these two compatibility requirements. To manage this constant flow of data between services, developers frequently default to textual, schemaless formats like JSON and XML. Because these formats don't enforce a strict structural contract, they appear highly agile. Omitting the schema, however, doesn't eliminate validation. It simply forces the application logic itself to parse the data, check for missing fields, and handle errors. Relying on implicit application layer schemas creates fragile data contracts. When traffic scales, these implicit contracts inevitably lead to bloated network payloads and unpredictable deployment failures. This image shows a standard JSON object for a user profile. It contains 3 simple keys: username, favorite number, and interests. Because JSON is a cross-language format, it must carry its structural definitions inside every payload. The actual data is small, but the literal strings outlining the field names take up significant space. Converting this object into a binary variant like MessagePack translates the data into a grid of hexadecimal bytes, which seems like a more efficient approach, but MessagePack remains schemaless. Without an external definition, the literal string names of every field must still be encoded into the payload. These specific bytes literally spell out username. When a service scales, that string redundancy is multiplied by millions of network requests per second across a cluster, consuming immense bandwidth to repeatedly transmit the exact same structural keys. True byte efficiency requires completely decoupling the structural definition, the schema, from the actual transmitted data payload. Binary encoding libraries like protocol buffers and thrift solve this by enforcing strict schemas that eliminate payload string bloat. This diagram shows how they use field tags. Instead of writing out verbose string names, the schema assigns compact integer aliases like 1, 2, and 3 to each piece of data. Replacing the strings with single bytes representing those tags collapses the payload down to roughly 33 bytes. These field tags also mechanically guarantee forward compatibility during a rolling upgrade. If the old version 1 code is scanning the byte stream and suddenly encounters a completely new integer, tag 4, it knows it has found an unknown field. Because the payload includes a data type annotation attached to that new tag, the parser determines the exact number of bytes it occupies. It jumps over the unknown data, lands safely, and continues reading the rest of the stream. For backward compatibility, the rules are similarly rigid. Developers can never reuse an old field tag, and they cannot remove a tag if the schema originally marked it as required. Explicit integer-based tag management provides mechanical certainty. Relying on exact string matching in JSON offers no such guarantees. Field tags act as an immutable mathematical anchor. They allow the data payload to shrink while enabling the application code to evolve independently, preserving the system contract. Apache Afro strips away even the field tags and data type markers used by protocol buffers. This animated diagram shows the resulting payload, pure concatenated values. It compresses the data stream to its absolute theoretical minimum. Curious, this raises an engineering question. How does a receiving application decode a raw byte stream that contains absolutely no structural identifiers? This layout illustrates Avro's requirement. The decoding application must have access to both the writer schema, which details how the data was originally encoded, and its own reader schema, which dictates how it wants to use the data. Avro uses a schema resolution engine to dynamically align the two schemas. It matches fields by name, ignores unknown data, and automatically fills in default values for any missing fields. By removing hard-coded tags entirely, Avro trades processing power at the resolution step for maximum network compression. This makes it a superior choice for dynamically generated schemas, such as exporting large-scale database dumps into long-term storage. Moving beyond the microscopic byte payload, we have to look at how these encoded formats travel across the deep strata of a system over time. The first major boundary is the database. This models the principle that data outlives code. A single database simultaneously holds records written 5 milliseconds ago and 5 years ago under different schemas. During read, modify, write cycles, older application code might silently delete newly added fields it doesn't recognize. Binary schema evolution prevents this. The old code safely retains the unmapped bytes in memory and writes the entire package back to the database intact. This inherent backward and forward compatibility eliminates the need to run expensive, system-halting database migrations every time a field is added. In storage environments, binary schemas ensure future code can reliably interpret and update data written by past versions, maintaining system continuity as the application evolves. The final boundaries of data flow are network requests and asynchronous message brokers. Modern microservices are built by entirely disconnected engineering teams, making impenetrable API contracts a necessity. This diagram shows how binary schemas act as mechanical validation boundaries. The broker uses the schema to verify the structure of every incoming packet, preventing one team's rogue deployment from transmitting malformed data and crashing a downstream team's service. Textual formats like JSON offer localized flexibility for an individual developer. Explicit binary schemas provide actual, systemic agility for the entire organization. By mastering byte-level data encoding and enforcing strict schema evolution, architects maintain the structural freedom to change without destabilizing the rest of the stack.